Cell 1. In this cell, we're setting the stage for optimizing last-mile delivery zones, an essential task for enhancing logistics efficiency. We're utilizing k-means clustering to identify optimal geographic centers for these delivery zones, which can have a significant impact on both operational costs and customer satisfaction. However, k-means alone doesn't take into account the capacity limitations that are crucial in real-world scenarios, such as the maximum number of stops or packages that each zone can handle. The logic here involves two primary steps. First, we employ k-means to group delivery stops into clusters that ideally represent these zones. This allows us to identify strategic central points for each zone. However, after initial clustering, we need to ensure that each zone adheres to predefined capacity constraints, like limiting each zone to a maximum of 120 stops or 2,500 packages. This is where our second step comes into play. We're introducing two different methods for achieving this reassignment of stops to clusters while enforcing capacity constraints. The first method is a fast heuristic approach that combines greedy selection with local swaps. This method is straightforward and requires no additional solvers, making it accessible for quick implementation. The second method is more refined and leverages advanced optimization techniques, such as minimum cost flow or mixed integer linear programming. This approach is cleaner and ultimately more effective, particularly if you have tools like OR tools or PULP at your disposal. Understanding these methods is vital because each has implications for the complexity and accuracy of your optimization. While the heuristic may be easier to implement, it may not achieve the optimal distribution that advanced techniques can offer. As we move forward to the next cell, we'll likely dive deeper into implementing one of these approaches, laying the foundation for a more nuanced understanding of how we can balance efficiency with practical constraints in last-mile delivery. Cell 2. In this cell, we're implementing a k-means clustering algorithm with a twist. We're adding capacity constraints to enhance our delivery zone assignments. This approach is crucial, not only for optimizing routes based on distances, but also for ensuring that each zone operates within its logistical limits, which can significantly improve efficiency. To achieve this, we first run the k-means algorithm to identify k-zone centroids, which serve as the central points for our delivery areas. We then move to the assignment phase, where each delivery stop is allocated to the closest centroid. However, this isn't a simple nearest neighbor task. We have constraints in place. Each zone has a maximum capacity, which could be measured in terms of the number of stops, total weight, or volume of deliveries it can handle. If a zone reaches its limit, any additional stops will spill over to the next closest zone, ensuring that we make the best possible use of our existing resources while still adhering to constraints. It's important to consider the trade-offs involved. For example, if one zone is filled while another is underutilized, we may end up with inefficiencies. Additionally, we have the option for local improvements through swapping assignments to achieve further reductions in total travel costs. This is a tactical step that can help fine-tune our delivery routes. Assumptions in this approach include the accuracy of distances calculated for zone assignments and the definition of capacity constraints. Learners should be cautious about how they define these constraints, as they can significantly impact the effectiveness of the algorithm. Looking ahead, the next cell will likely build on this framework by introducing additional features or refining the optimization process, potentially incorporating more advanced algorithms or heuristics to further enhance our delivery efficiency. This progression is crucial for making our logistics operations smarter and more adaptive to real-world challenges. Cell 3. In this cell, we're utilizing k-means clustering to effectively categorize demand points based on their geographic locations, helping us understand how to allocate resources across specific zones. This method is particularly pertinent for optimizing operations, such as delivery services, by ensuring that each zone can efficiently handle the demand it has while maintaining capacity limits. The workflow starts by defining the essential structure of our data. The function k-means then capacity assign takes a data frame that includes latitude, longitude, and a demand column. If specific zone capacities are provided, the function calculates them based on the total demand and the number of zones, ensuring they're evenly distributed. After establishing the necessary parameters, k-means is deployed to identify initial centroid points, representing each zone center. Once the zones are established, we compute distances from each stop to these centroids using the calculated Haversine distance formula, which accounts for the Earth's curvature, making it ideal for our geographic data. This distance metric is crucial because it allows us to prioritize assigning stops to the nearest available zones. Next, we move into a greedy assignment process, where we aim to fulfill demand by prioritizing stops that have fewer alternative options based on distance. By ranking the stops according to how far they are from their nearest alternatives, we strategically place them in zones with available capacity. If a stop cannot be assigned due to insufficient capacity, the function raises an error, prompting the user to reevaluate their zone configurations or capacities. After zones are assigned, we enrich our data frame with additional information about the distance each stop is from its assigned centroid. We also compile a zone summary that consolidates crucial statistics, like the number of stops per zone, used capacity, and average distances, providing a comprehensive view of each zone's performance and capacity utilization. Additionally, a demonstration dataset simulating demand points around a city center is generated for testing purposes. By executing the function with this sample data, we can visualize how the zones are filled, alongside the central data about each zone's demand and capacity metrics. In the upcoming cell, we'll likely delve into analyzing the results from our clustering method, potentially exploring visual representations of the zones and their capacities to better understand the dynamics at play. Cell 4. In this cell, we're generating a simulated dataset that mirrors demand points you might find around a city, which is critical for understanding how clustering algorithms can effectively manage service or resource allocation. By creating a dataset with specific parameters, we set the stage for experimenting with the spatial distribution of demand. Starting off, we employ NumPy's random number generator to ensure that our results are reproducible. Here, we define the number of data points as 1,200, which is a reasonable size for our demonstration. To mimic a real city environment, we establish a central latitude and longitude for the city center, specifically the coordinates of New York City. Using the normal distribution, we introduce small variations in both latitude and longitude to generate demand points that are clustered around this center. This randomness simulates the idea that demand is not evenly spread out, but rather concentrated in certain areas. The dataset also incorporates a demand column, where we randomly assign values between 1 and 5 packages per stop, representing the varying needs at each location. Once we have this data frame constructed, we're ready to utilize the k-means clustering algorithm. In this step, we divide these demand points into 10 zones, each with a defined maximum capacity of 450 packages. We call a function that not only performs the k-means clustering, but also assigns these demand points to the respective zones, while considering the predefined capacities. The outputs from this function, including the assigned data frame, centroids of the clusters, and a summary of how the capacities are utilized, are crucial for assessing the effectiveness of our clustering strategy. It's important to note that assumptions around normal distribution and capacity constraints might impact our results, so careful evaluation will be necessary. In the next cell, we'll likely explore how these assigned zones function in practice, possibly investigating the implications for resource allocation or service optimization based on the clustering we just implemented. This sets up an intriguing pathway for further analysis of demand management. Cell 5. This cell is designed to create an engaging visual representation of last-mile delivery zones along with their centroids using Plotly, an interactive graphing library. The visualization helps users better understand the spatial distribution of zones and their respective centroids, which can be vital for logistics and planning. The process starts with the initialization of a scatter map box, where we pass the relevant data from a data frame called assigned DF. The latitude and longitude columns specify the positions of the delivery zones, while the zones themselves are color-coded for clarity. We also incorporate a size attribute that correlates with demand, enabling viewers to immediately grasp where the highest demands lie. Hovering over any point reveals additional information like the stop ID, demand, and distance to the centroid in kilometers, enhancing user interaction. Next, centroids are prepared by copying the existing data and adjusting their size to create a clear visual separation from the delivery zones. The centroids are then plotted on the same map, which allows for direct comparison between the locations of delivery zones and their centroids. One key point to note is that these centroids are represented as star markers, effectively distinguishing them from the zones, and this is accomplished through a loop that updates each trace accordingly. The finished layout uses a clean map style called cartopositron, providing a visually appealing background that enhances the data presentation. However, it's worth mentioning that while the resulting visualization might look intriguing, it carries a risk of being misleading if one misinterprets the clustering or distribution of zones around central Manhattan. This leads us to consider how the next cell may build on this visualization, perhaps by delving deeper into the analysis of zone efficiency or providing insights on optimizing delivery routes based on the depicted data. Cell 6. In this cell, we're taking a significant step forward in our analysis by generating stops directly on the road network of New York City, which is essential for any transportation or urban planning study. This approach gives us a realistic representation of potential stop locations, helping inform decisions about transportation services and infrastructure. We start by importing the necessary libraries, with OSMnx being central to retrieving the city's road network. After defining our area of interest, New York City, we create a directed graph representing this network, specifically designed for driving. We then project this graph to ensure that our coordinates are accurate. The next logical step involves converting this graph into a geodata frame that contains our road segments. Here, we filter the edges to focus solely on line geometries, which represent the actual roads, and we calculate their lengths. This measurement is crucial since we want to sample road segments in proportion to their length, ensuring that longer segments have a higher probability of being selected. With a total of 1,200 segments to sample, we introduce randomness to our selections using a fixed random seed to ensure reproducibility. This will ultimately allow us to create stops that are distributed fairly across the road network. After selecting the segments, we generate random points along these chosen lines, utilizing a helper function designed to deal with both line strings and multi-line strings effectively. Each selected road segment yields a specific number of stop points based on the segment's proportionate length. The next part of our workflow involves creating a geodata frame that pairs each stop with its geographical coordinates and a simulated demand value, which we generate using a random integer function. This aspect adds a layer of realism, enabling us to model potential usage at these stops. As we prepare for the subsequent analytical phase, we implement a zoning strategy that organizes these stops into distinct zones, each with their capacity. Using k-means clustering methods, we aggregate the stops into 10 zones based on their demand characteristics. Finally, we visualize the results using the Plotly library, creating a scatterplot that illustrates the stops colored by their zone identification. This dynamic and interactive visualization allows us to see the geographic distribution of stops and their associated demand, laying the groundwork for deeper analysis and optimization in later cells. Moving forward, the next cell will likely focus on analyzing these generated stops and their assigned zones to derive insights into service efficiency and demand distributions in the city. Cell 7. In this cell, we're creating a bar chart that visualizes the usage and maximum capacity of different zones. This visualization is crucial because it allows us to quickly assess how much of each zone's capacity is being utilized, helping identify potential areas for improvement or reassessment of resource allocation. The first step in our process involves sorting the zone summary data by the variable representing used capacity. By arranging the data in descending order, we glean insights into which zones are at or near capacity, thus highlighting stress points within the system. We then set up a figure using Plotly, a powerful library for creating interactive visualizations. Next, we add a bar chart to represent the used capacity for each zone, making it easy to see at a glance how much capacity is currently being utilized. Alongside this, a line graph illustrates the maximum capacity for each zone, using both markers and lines to enhance the clarity of the comparison. This dual representation allows us to visualize not just the current usage, but also how it relates to what's possible. We then define a layout for the chart, including a title that conveys the purpose of the visualization and labels for the X and Y axes, giving context to what the bars and lines represent. The height of the chart is also specified to ensure it's visually accessible. When executing this cell, it's important to keep in mind the accuracy of the data in zone summary, as any discrepancies there would affect our insights. The interactive nature of the plot will enable us to click through different zones and gain immediate feedback on capacity concerns. Looking ahead, the next cell likely will build on this visualization by diving deeper into the implications of this data, perhaps analyzing trends over time or comparing across different parameters. This will further enhance our understanding of the operational dynamics of each zone. Cell 8. In this cell, we delve into the important interplay between geography and workload management within the k-means clustering framework. While k-means is effective in creating compact geographic zones, It often overlooks the crucial aspect of balancing workload across these zones. This limitation can lead to unequal distribution of tasks, which is something we want to address. To tackle this, we propose using k-means not as the final solution, but rather as a foundational starting point, or seed, for our next steps. The idea here is to refine those initial clusters by incorporating capacity constraints that ensure each zone can handle its assigned workload effectively. By doing this, we are aiming to create zones that are not just geographically logical, but also operationally viable. The key elements in our approach include defining a distance-to-centroid as our cost function, which acts as a proxy for estimating drive times within these zones. This serves to minimize travel distances for tasks assigned to each region. Additionally, we must take into consideration the capacity limits of these zones. After all, if one zone is swamped while another sits idle, we haven't achieved true balance. It's crucial to remain aware of the assumptions we make throughout this process. For instance, we assume that workload capacity can be reasonably estimated and that the initial k-means clustering adequately reflects geographic realities. Misestimations here could lead to ineffective zone assignments, skewing our desired outcomes. As we look ahead to the next cell, we'll build upon this nuanced understanding of zone design to implement the actual capacity-aware assignment step. This will further refine our model and push our exploration of balancing both geography and workload. Cell 9. In this cell, we're implementing an advanced method for optimizing delivery zones by leveraging a network optimization approach. This approach is essential for efficiently assigning stops to respective zones while considering various constraints, such as delivery capacities and driving time. To start off, the function defined here takes in a data frame containing stop data, including geographic coordinates and package loads. It utilizes k-means clustering to establish centroids for a specified number of zones, which helps efficiently organize stops based on their geographical proximity. The Haversine formula plays a crucial role in calculating distances between each stop and its assigned zone centroid, transforming this geographical data into a format suitable for optimization. The core logic pivots around building a directed graph to represent the relationship between stops and zones. The function sets up nodes for the source and sink, where the source represents total demand and the sink stands for the capacity of each delivery zone. A critical decision here is how we determine connections. We only connect each stop to its nearest zones, significantly trimming down the complexity of our graph, while still ensuring feasible allocations. As we apply a minimum cost flow optimization algorithm, the graph structure allows us to efficiently direct package loads to their designated zones without exceeding capacity limits. After solving this flow model, we identify which zone each stop is assigned to, and ensure no stop is left unassigned, barring any errors stemming from previous pruning tactics. The end result feeds back into our data frame, merging in the calculated centroids and distances. We also summarize the information at the zone level, highlighting key metrics, such as total stops and average distances. It's essential to note that while this process assigns stops to zones, it doesn't delve into the sequencing of visits, an area we might explore in subsequent cells. On that note, as we progress, we'll shift our focus from just assignment to examining the optimal routing of sequences within each zone, a critical aspect in real-world delivery logistics that ensures drivers can operate efficiently. Cell 10. In this cell, we're about to analyze the current load capacity status of our zones and understand the implications for future logistics. This assessment is crucial because it allows us to identify which areas are at or near capacity and which ones still have room to accommodate additional loads. We start by noting that certain zones, specifically zones 0, 2, and 5, have reached full capacity, indicating that they can no longer take on additional loads without spilling over into other areas. This situation leads us to consider the effects that an augmented load will have on the overall distribution of capacity. Zone 4 is nearing its limit as well, leaving only a small buffer for additional work. Meanwhile, Zone 1 shows significant slack with many available resources, indicating a potential area for load balancing. This disparity in usage raises critical questions about our approach to capacity management. On one hand, we have zones that are geographically compact, facilitating easier access and potentially lowering costs. On the other hand, the saturation of certain zones can necessitate spillover into less optimal areas, which may lead to increased travel distances and costs. In this cell, we'll proceed with two primary steps. First, we will assign a cost to our current distribution model, which will help us quantify the impact of the existing setup. Then, we'll aim to create a more optimal scenario and compare the costs associated with each. This comparison will illuminate potential inefficiencies in resource allocation and enable us to make more informed decisions moving forward. As we explore these calculations, it's essential to keep in mind the balance between compactness and feasibility. Understanding these dynamics will prepare us for the next steps in refining our logistics strategy, highlighting the pathways we can take to optimize our capacity use across the different zones effectively. Cell 11. In this code cell, we're tackling a complex optimization problem involving the assignment of delivery stops to geographical zones. The goal is to distribute packages efficiently, minimizing the associated costs based on travel distances and service times. Key to this process is the use of the k-means clustering algorithm to determine the initial zone centroids. The function begins by implementing the Haversine formula to calculate the distances between stop locations and zone centroids. This mathematical approach ensures we're working with accurate geographical distances, which is essential for the next step involving k-means clustering. If we're seeding the zones using k-means, the coordinates from our data frame will help create centroids, which represent the geographical centers of our zones. This lays the groundwork for assessing how to best allocate resources. Following the establishment of centroids, we shift focus to calculating the costs incurred for potential deliveries. This involves not only computing the driving time based on distance, but also considering any service time associated with each delivery. If the specific service time column is absent, a default value is used, which simplifies the process but could affect results. As we proceed, total minutes of delivery are computed, leading to the overall cost associated with transporting packages from stops to zones. Next, we consider the loads that each stop generates. This part involves validation to ensure that the capacities set for each zone are sufficient to accommodate the demands placed upon them. We use NetworkX to create a directed graph, where zones are treated as transshipment nodes and stops are the demand nodes. It's crucial that we limit connections to only the nearest zones to optimize the graph and avoid excessive computational load. Finally, the function applies the min-cost flow algorithm to determine the assignment of stops to zones, ensuring that all loads are appropriately allocated. The assignments yield a data frame with detailed delivery information, including distance to centroids and total estimated delivery time. The generated zone summary provides insights into each zone's capacity and operational efficiency, allowing for more informed decision-making. In moving forward, the next cell will likely unpack this assignment data to analyze its effectiveness. We'll delve deeper into the results, interpreting how well the assignments align with our initial goals, and possibly refining our zone capacities or the clustering parameters based on the insights we gather. Cell 12. In this cell, we're diving into the optimization of our zone assignments by calculating the flow optimal cost of transporting packages, which is a crucial step in our overall analysis. Achieving an efficient cost model not only impacts the bottom line, but also enhances service delivery, making it a vital aspect of our logistics strategy. The process begins with invoking a function that aims to minimize costs associated with package distribution across defined zones. We pass in our demonstration data frame, specifying 10 zones, along with other necessary parameters, such as the number of packages, individual zone capacities, travel time per kilometer, and service time. Each parameter plays a significant role in defining our network's operational limits and efficiency. Next, we build a cost matrix using the optimized assignments and centroids we derived. This matrix becomes a pivotal tool in quantifying costs associated with different routes and load distributions. Following that, we calculate the cost associated with the optimal flow using another function specifically designed for this purpose. It evaluates the total expenditure for our scenario based on the flow assignments and the specific routes identified. As we execute the code, we're particularly interested in two outputs: the optimal flow cost and the improvement over our previous cost calculation. The difference between these two values will illuminate how effectively our optimization has reduced expenses, offering a quantitative benchmark for evaluating performance. A sober note to consider here is that the assumptions made during the assignment process, such as the chosen capacities and time parameters, can influence our results significantly, underscoring the need for good data quality and realistic constraints. As we analyze the print statements, they'll reveal our flow optimal cost and highlight the savings achieved versus the current operational costs. This gives us a concrete goal to aim for in our optimization efforts. With these insights in hand, we set the stage for the next cell, which likely seeks to implement further analysis or perhaps refine our zone assignments based on additional data or constraints. This continuous improvement mindset will drive us deeper into understanding and optimizing our logistics processes. Cell 13. In this cell, we're focusing on constructing and optimizing a route for a specified zone, using some key algorithms and mathematical techniques. Utilizing the nearest neighbor approach and the two-opt improvement method, we aim to find an efficient way to visit a series of stops, which is particularly useful in logistics and transportation scenarios. The process begins by defining helper functions to calculate distances using the Haversine formula, which considers the curvature of the Earth, ensuring we get accurate distances between geographic coordinates. Next, we construct a distance matrix with these coordinates, enabling us to evaluate how far apart the stops are. The nearest neighbor algorithm is employed to generate an initial route by repeatedly choosing the closest unvisited stop. This method is straightforward but can be improved. Once we have the initial route, the two-opt algorithm refines this path. It works by checking pairs of nodes along the route and reversing segments when it results in a shorter overall distance. This iterative process continues until no further improvements can be made, ensuring that the route is optimized as much as possible while adhering to the constraints stipulated. When we build the route for a given zone, we have to decide the starting point. Depending on the chosen mode, either the closest stop to a zone centroid or simply the first stop, we set up our routing parameters. If a zone contains fewer than 2 stops, we skip routing entirely to avoid unnecessary calculations. Finally, this cell concludes by displaying the optimized route, including details such as the total number of stops and the approximate distance of the route. Looking ahead, the next cell will likely delve into evaluating this optimized routing approach further, perhaps exploring how it performs against different parameters or comparing multiple zones, allowing us to assess the efficiency improvements achieved. Cell 14. In this cell, we're focusing on visualizing a drivable route across a specific zone in New York City, effectively connecting various stops while adhering to the actual street network. This step is crucial because it ensures that our plotted path is not only accurate, but also practically traversable. To kick things off, we utilize the OSMnx library to create a street network graph for the area, specifically tailored for driving. We also enhance this graph by adding information about edge speeds and travel times, which will become instrumental in determining our route's efficiency. Next, we have a key function designed to snap our predefined route stops to the nearest road nodes. By doing this, we ensure that each stop aligns with actual road points instead of floating arbitrarily. The function first identifies the closest nodes and then merges this data back to include their geographic coordinates in our data frame. After ensuring that our route stops are correctly placed, we proceed to generate a street-following polyline. This is where another function comes into play, which takes the ordered stops and calculates the most efficient path between them. By leveraging the street network, we determine the total travel time while accumulating the coordinates that will later be used for plotting our route. Moving forward, we compile the results for a specific zone. In our current scenario, we're concentrating on Zone 0. We begin by snapping the route points to the network, ensuring they are fit for driving. The next step involves constructing a road-following polyline that outlines the actual path we'll take. Finally, we utilize Plotly to create an interactive map that showcases both the snapped stops and the street-following trajectory. This visual aid enriches our understanding and makes it easier to analyze the route's effectiveness. With the plotted route in front of us, our next step will likely involve analyzing this path further or considering optimization strategies based on the visual feedback we've gathered. Cell 15. In this cell, we are delving into a fundamental optimization task where we compare the distances of a baseline route against an optimized route using a traveling salesman problem heuristic. This comparison can be crucial for logistical planning, ensuring that routes are as efficient as possible, thus saving both time and resources. To start this process, we first compute the baseline route length based on the current order of stops. This initial route is derived from a data frame, which is prepared for a specific zone we're evaluating. After determining the sequence of stops, we utilize a helper function to calculate the total distance of this baseline route from our graph representation. The output is displayed in kilometers, which provides an intuitive grasp of the route's length. Next, we shift gears to find an optimized route using a TSP heuristic, which seeks to minimize the route distance by intelligently rearranging the order of stops. The approach involves creating a complete graph that captures all possible routes between the stops, where the weights of the edges represent the shortest path length on the street network. We carefully iterate through these nodes, calculating the distances between each pair, which allows us to formulate an efficient path. Once we have this optimized order, we map it back to a data frame for further calculations. Similar to the baseline route, we compute the distance of the optimized path, and importantly, we also derive the improvement made by comparing the two routes. The results reveal not only the distance of the optimized route, but also the percentage gain compared to the baseline, giving clear insight into the optimization's impact. One key consideration here is that learners should be cautious of potential pitfalls, like ensuring the nodes are correctly snapped to graph nodes, which is crucial for accurate distance calculations. With these preparations and computations complete, we set the stage for our next steps. The subsequent cell is likely to build on these insights, potentially exploring how to visualize these routes or applying further optimizations. Cell 16. In this final cell, we're wrapping up our analysis, marking the completion of our exploration. It's essential to reflect on what we've accomplished and consider how the insights gained will guide our next steps. At this stage, we have gathered valuable data, processed it, and drawn meaningful conclusions. This cell emphasizes not just the end of our current tasks, but also the importance of what we've learned throughout this notebook. We've dived deep into the relationships and patterns within our dataset, ensuring that any assumptions were carefully scrutinized. One thing to keep in mind is that while this marks the end of our current analysis, it also lays the groundwork for future inquiries. Any findings can serve as a springboard for further research or new questions to investigate. This iterative nature of data science emphasizes that even when one task is complete, new opportunities are always on the horizon. By wrapping everything up here, we're setting ourselves up for future projects that might require a similar methodology or exploration technique. So, as we transition to what comes next, let's remember that every conclusion is merely a stepping stone to a deeper understanding or a new direction. In the upcoming cells, we will likely build on this foundation, possibly by applying what we've learned to new datasets or different analytical methods.